Today, we are talking about something that feels like it's straight out of science fiction, a genuine mathematical earthquake, a problem that has been officially unsolvable for 200 years. Well, it just got solved. And trust me, this isn't just about some new formula. It's about completely rewriting the rules of what's even possible. So let me just ask you this. What if a whole class of math problems that have been proven, literally prove it to be impossible to solve exactly, suddenly weren't? What if that proof of impossibility wasn't the final word after all? Because a new method has just shown up that finds perfect, exact answers to these so-called unsolvable problems.
Now, to really get how huge this is, we've got to go back in time. For centuries, mathematicians were on a roll. They were solving more and more complex equations, and it really seemed like nothing could stop them. But then they hit a wall. A door was slammed shut, and for 200 years, that door stayed locked.
I mean, just look at this timeline. You can see the progress building. Most of us probably remember the quadratic formula from school, right? Well, by the 1500s, they'd cracked the next two levels up for third and fourth degree polynomials. The momentum was unstoppable. It felt like a universal formula for any degree was just right around the corner. And then, in 1824, everything just stopped.
And this is why. The Abel-Ruffini theorem. This wasn't some mathematician saying, gosh, this is really hard. This was a formal mathematical proof of impossibility. It proved that you could never find a general formula using standard tools like addition, multiplication, and roots, what mathematicians call radicals, for any polynomial of the fifth degree or higher. For 200 years, that was the end of the story. Case closed.
So, what happens then? I mean, science and engineering couldn't just throw their hands up and stop. The world had to adapt. And so, we settled. We settled for good enough answers, using methods that gave us really, really close approximations. But as we're about to see, good enough has some serious hidden costs.
And here's the trade-off we've been living with. These approximation methods are clever for sure, but they're basically built on educated guesswork. They introduce these tiny, tiny rounding errors that can build up and sometimes cause huge instabilities in complex systems. But the biggest thing is, they can never give you the exact, beautiful symbolic answer. They give you a long decimal that's close, but they can't tell you the underlying mathematical truth. But what if we didn't have to settle for close enough anymore? In 2023, a brand new method appeared. And the crazy thing is, it doesn't break Abel's theorem. It just goes around it. It completely sidesteps the old limitations by playing in a whole new mathematical sandbox.
And this is the key. Ezouidi's theorem doesn't actually violate Abel's theorem. See, Abel's proof was all about the impossibility of finding solutions using those radicals we mentioned. Ezouidi's method uses a completely different toolkit, a really powerful step-by-step process called recursion to build the exact symbolic answers without ever needing those classical tools.
This table really just lays it all out. The old ways hit a hard wall at degree 5 and are always haunted by errors from approximations. But Ezouidi's theorem? It works for any degree, spits out perfect symbolic answers, has literally zero error, and you can apply it to anything. It's not just an improvement, it's a total paradigm shift.
Okay, so how does this magic recursive engine actually work? Now don't worry, we are not about to get lost in a sea of complicated formulas. We're just going to look at the elegant idea that makes the whole thing tick. First, let's just appreciate the scale of the problem here. The source paper for this new theorem takes on this absolute monster, a 19th degree polynomial with ridiculously complex coefficients. Trying to solve that with the old approximation methods would be a total minefield of errors. But for this new theorem, this is just another day at the office. The process itself is surprisingly elegant. First, you just identify all the coefficients in your equation. Then, you take this special recursive formula and apply it, again and again. Each time you run it, it generates a new symbolic value. And once you've done that enough times, you use this new set of values to perfectly construct the exact roots. It's that simple.
You can almost picture it like a sophisticated mathematical assembly line. Each step takes the output from the last one, does its little job, and passes it along, systematically building towards the final solution. The real magic is in how structured and repeatable it is, which guarantees a perfect result without any guesswork at all.
Okay, now here comes the best part. After all those recursive steps, and for our example, that's 19 of them, something amazing happens. The vast majority of those new symbolic values it generated, they turn out to be zero. And this reveals a hidden, much simpler structure that was buried inside that original complicated equation all along. And this is what that massive 19th degree polynomial simplifies into. It's an incredible transformation. Right away, you can see one root is just 0. And the rest, well, they can be found by solving what's basically a simple quadratic equation now. All that initial complexity has just been elegantly dismantled.
And from this beautifully simplified form, the method delivers the exact roots. We're talking precise symbolic terms. There are no trailing decimals, no rounding, no close enough. This is the true algebraic answer. The very thing we were told for 2 centuries was impossible to find.
So remember that door that the Abel-Ruffini theorem slammed shut back in 1824? Well, it is officially open again. And it wasn't kicked down by brute force. It was opened with an entirely new kind of key. This really does feel like the beginning of a new era in mathematics. The implications here are just profound. We now have a way to find perfect answers where we used to be stuck with approximations. The very idea of an unsolvable high-degree polynomial is kind of obsolete now. But maybe the biggest lesson of all is that sometimes the biggest walls in science aren't the problems themselves, but just the way we've been taught to look at them.
This whole story is just such a powerful reminder to question our assumptions. A 200-year-old barrier in math didn't fall because someone tried harder. It fell because someone tried different. And that leaves us with one last, really exciting question. What other impossible problems out there are just waiting for us to find a new way of looking?